Okay, in the previous lecture we have discussed about the basics of the SAR ADC. So we'll continue with that. So now we will discuss about an implementation, a switch capacitor based implementation of the SAR ADC is basically the charge redistribution based SAR ADC. Okay, so before we start about the discussion, just let's revise some of the basic things that we have discussed in the previous lecture, and then we will do a small modification before we proceed ahead with the discussion of the charge distribution redistribution based SAR ADC. Okay, so what we had discussed was, so we had suppose if I have a this one, if I have a BREF, which is my full range, okay, full scale voltage, okay, and we have if suppose for n equal to 3 we have considered an example, and we have divided into the 8 equal segments, okay. So and what we have told is that if it is lower than this one, then this is 0 0 0, then this is 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, then 1 1 1. Okay, so this threshold voltage we're defining this this different levels. Okay, so and if you remember, we had started with the first one was to decide this MSB is we have kept the threshold of the VD to A converter as VREF by 2, and what we have used a comparator, and where we have compared, okay, V in with respect to this VD to A output. Okay, so I have my V in, and here we have the VD to A output. So we started with VREF by 2. Okay, and then of course if my point is higher than this one, okay, on this point, then this is 1, else it is 0. Okay, so this is what we have been discussed. Okay, so the same thing, the same representation I can do it in a little different way. So instead of using the comparator something like this, especially in the source redistribution based architecture, what we are going to do is, we are, instead of comparing with V in with respect to VREF by 2, we are going to compare V in minus VREF by 2 with respect to 0. So this is the same thing, right? Whether I am comparing V in with VREF, or the difference between V in and VREF with 0. Okay, so that means if it is the V in minus VREF is higher than 0, that means this is going to be 1, that means my V in is greater than VREF, and vice versa. Okay, or I can still do a small modification, and I can even interchange these notations. So if I make it this plus and minus, okay, and this with respect to ground, so that means here I can write it as, I can just subtract V in plus VREF by 2. Okay, it's just multiplying with minus 1. So again, they all are equivalent. Okay, okay, so the other thing that I would like to mention here is, okay, so the other thing that I like to mention here is, we started with VREF, okay, and suppose if my V is equal to 1, what we did is, we went to this point and we told that the next reference voltage that I'm going to compare will be VREF by 2 plus VREF by 4. Okay, whereas if it is 0, we went to this value, okay, and this is nothing but, again, we told that VREF by 2 minus VREF by 4. Okay, so but this one, can I write directly as instead of just writing VREF by 2 minus VREF by 4, we can just directly write as VREF by 4 directly, okay, plus VREF by 4. Okay, so because VREF by 2 minus VREF by 4 is VREF by 4 only. That means, what it means is that if the MSB is 1, my next threshold for comparison will be VREF by 2 plus VREF by 4. Whereas if it is 0, I can just directly go to VREF by 4. Okay. Similarly, from here also, if we go to the next, if in this case, if it is 1, if it is in the higher side, then it becomes, this point becomes VREF by 4 plus VREF by 8. Whereas if it is 0, I can directly go to this point, which is Vref by 8. Okay, so the conclusion here is that, okay, this summation of Vref by 4 plus Vref by 2 plus Vref by 4 plus Vref by 8, it happens only when the previous one is previous bit is 1, whereas if it is 0, I can just directly use the Vref by 4, or whatever. Yeah, so that's how we are going to update the VD to A. Okay, so as things unfold, things will be more clear. Okay, so just remember this one. Okay, so that that if it is 1, then only we are going to add it, otherwise we are just going to use this one. Okay, so yeah, so this point will be used in the charge redistribution based architecture. Okay, okay, so let's draw the structure of the charge distribution based architecture. Okay, so I have my comparator here. Okay, and the positive side of this comparator, or it's basically an op-amp. Okay, high gain op-amp. It is fed to the positive side of this op-amp, and as a feedback there will be a switch here. Okay, so in some mode this switch will be on, and in some other mode this will be off for this op-amp. Okay, then we have let's consider maybe a 5-bit ADC. Okay, so or 5-bit SAR ADC. Okay, so then there will be this capacitor. Okay, so and this will have a switch here. This is grounded, and this switch. Okay, so let me throw all this first. Okay, so these are the switches, and let's give some name to these switches. Okay, so this is my bit B1, B2, B3, B4, and B5 for this 5-bit ADC. Okay, and of course the value of this capacitor is 16C, this is 8C, this is 4C, this is 2C, this is C, and C. Okay, and we have one more switch here. Okay, so this switch will be either connected to my V in, or it will be connected to Vref. Okay, and there are basically 3 more switches here if you see. So let's name this switch as S1, this as S3, and this as S2. Okay, so depending upon what is the mode of operation, okay, so we will be turning these switches. Okay, this one. Okay, and if this B1 is equal to 1, it will be connected here. Okay, else it will be connected to the ground. Okay, similarly it happens to B2, B3, B4, B5. Okay, and eventually what happens is there will be a digital logic. Okay, so digital logic or the SAR logic. Okay, this SAR logic or the SAR algorithm basically, so that will be controlling all these switches. Okay, so that will be controlling all these switches. This was switches and S1, S2, S3, and then B1, B2, B3. So that will be controlling all these switches. Okay, basically it will be controlling the B1 to B1, B2, B3, B4, V5 and of course S1, S2, S2 and S3. Okay, yeah. So now let's go to the different modes of operation. Okay, so we'll go one by one to all the different modes of operation. Okay, the first mode is the sample mode. Okay, so let me copy this one. So the first mode is the sample mode. Okay, so in the sample mode, okay, my S1 is connected like this. Okay, then of course this all these are connected to this way. Okay, this all are connected as on this one, and of course these S2 also will be on. Okay, so in this case what will happen is my this voltage Vx, if you see here, this is more like this in a feedback, like unity gain feedback kind of configuration, and because this voltage is 0, so here this will be approximately equal to 0, virtually grounded. Okay, this is virtually grounded, and if you see here, this configuration is equivalent of as if you see the what I'm trying to do here is that I'm having a here. Okay, this is if I draw the equivalent kind of circuit, it is something like this. This is going to approximately 0, and I am having a capacitor here. So the total, all the capacitors are coming in parallel. So if we add them, it will be 32. This is 2, then 4, then 4, 8, 16, then 32. Okay, so this is 32C. Okay, and then other side it is connected to V in. So this is my equivalent configuration. Okay, so one side of the capacitor is connected to V in, the other side of the capacitor is connected to this virtual ground. Okay, so this is my sample mode. In the hold mode, what I will do is I will suddenly open the switch. Okay, I'll suddenly open the switch and then release the release the V in, and of course we'll connect it to some other voltage that we'll see. Okay, so I will just open the switch. Okay, as a result of which whatever the voltage or the charge that this capacitor has stored, so that will be held in this capacitor. Okay, so that's is in the next stage, which is called the, after the sample we'll have the hold mode. Okay, so let's go to the hold mode of operation. Okay, so now we'll discuss the hold. Okay, we have gone to the sample. Then in the hold mode, what we are going to do is, okay, we have sampled it. Okay, so instead of we are going to release this. Okay, so this will be open. Okay, so what we had seen is this was initially 0. Okay, so we will open it, and then what we'll do is we'll connect all these switches, right? All these switches, all the switches will be turned to 0. Okay, so in the hold mode, okay, so after we release this switch, okay, so then we are going to make all of them to 0. Okay. So they are connected to 0, 0, 0, 0, 0, 0. So basically this wire is disconnected, and of course here we are going to switch this one to Vref as well. The reason is, although now this S2 is, this whole wire is disconnected from this capacitor, but we are preparing for the next stage. So this S1 will be connected to this Vref. Okay, so now the whole thing is disconnected from V in. Okay, and as I was mentioning that this S2 is open first before disconnecting or turning this connecting these switches to the ground. Okay, so in this case what we will see is how does the circuit looks like. So it looks like something like this. Okay, so now my op-amp is disconnected, or the feedback of this op-amp is disconnected. Okay, this is plus minus. Okay, and what I'm having now is again all the 16 capacitors are there, and this is something like this, and this is suddenly connected to the ground. So this again 32C. The question is, what about this voltage? Okay, so initially this capacitor has already charged the Q that is there in this negative side of the plate is already equivalent to the Q will be C into V. Okay, C into V in. Okay, so that means and now we have connected this to the ground, but this charge which was already stored in the sample mode, it will be it will be there, because first we have released this one and there is no way for a charge to flow here. So this voltage will become minus V in, or if I call this voltage as Vx. Okay, so this line, this Vx will be equal to minus V in. Okay, the reason is because we have first released this S2. Okay, we have first released this S2, this one open, and then because already the charge is there, and suddenly we have connected to this ground, so the whole polarity of these capacitors get reversed, and because there is no path for the charge to flow if I am removing the switch. Okay, that's why the polarity gets reversed, and this polarity becomes, this Vx becomes, from 0 it turns to minus V in. Okay, yeah, so this is the case of the whole mode. Basically now this Vx is holding this Vx as minus V in. Okay, so now the next stage after this that we are going to do is the bit cycling stage. Okay, so let's copy this one and then go to the next page. Okay, so now we have this V in. Okay, so maybe just okay, so now what we have opened this one, this is minus V in. Okay, so now the next, this cycle is called as the beat cycling stage. Okay, so in the beat cycling stage, what we are going to do is that the first thing that we are going to do is we are going to just change this switch B1 from 0 to, we are going to change it to from 0 to here. We are going to make it from 0 to 1. Okay, so now that means if you see this 16C capacitor is going to get connected to Bref, whether all the other capacitors are connected to the ground. Okay, they're still connected to the ground. So now this Bref will this will connected to Bref. Okay, so now the question is, what happens here? Okay, what happens to this voltage? Okay, so now if you see here, if you see the configuration, assuming that initially the capacitor is not charged, or assuming that there is no V in is there, if you just see this one, this capacitor redistribution, it is something like it is something like, you see, I have a 16C here, and I have this remaining, this whole is also 16C. Okay, so it is something like of course this op-amp is there. Okay, so if I imagine that all these capacitors are not charged, okay, and it is, then what I have done is I have just redistributed it. Or these capacitors are connected to the ground. Okay, and equivalent is 16C, and then I have one other capacitor which is connected through this 16C to the Bref, which is connected to the S1. Okay, so if I imagine that initially these capacitors was chargeless, and I have just applied some voltage here, that means this is going to become Bref by 2. Okay, this voltage is going to become Bref by 2. Okay, this is a basic simple capacitor calculation. Okay, but now because this voltage was already, in this case this voltage was already minus V in, so what happens is that in this case it is just nothing but the superposition of this one and this one. Okay, so that means that now my, in this case, when my Vx is already minus V in, so in this case when I just turn these switches from, from 0 to 1, this becomes, so the voltage is simply going to get added, okay, Vref by 2. Okay, so now we have the Vx as Vref by 2. So now if you see here, I can compare it with this voltage. So if my V in is greater than Vref by 2, okay, so that means this voltage is going to become negative, okay, because V in is greater than Vref by 2. That means, and because I am connecting this to this one negative, so then this becomes 1. Okay, so we are basically now trying to do this comparison. So if V in is greater than Vref by 2, this becomes 1, whereas if V in is less than Vref by 2, this becomes 0. So we are basically doing the first comparison of the SAR ADC. So if you see here, we are doing this one, we are doing this one, and then we are trying to do the comparison. So first we are doing the, making the basic comparison of the Vref by 2. Okay. Yeah. So this is the bit cycling stage. Okay. So now, as I was mentioning that if suppose during this comparison, if the V in is happens to be greater than Vref by 2, then what we are going to do is we are going to maintain this V1 equal to 1. Okay. Else we are going to turn it to 0. Okay, so yeah, else we are going to turn it to 0. Okay, so yeah, so now suppose let's assume that in this case V1 is V in is greater than Vref by 2, and we have got it 1, and we just maintain it. Okay, the next thing that we are going to do is we are going to now change this one to B2. Again we'll just check to 1 and see what is, whether this is 1 or 0. Okay, so now as soon as this B2 is connected here, okay, so now what will be the voltage here? The same thing can be applied here. Okay, so in this case if I assume that if we so if we okay, let's draw the equivalent circuit, then things will be more clear. So in this case again I have this op amp here, okay, minus plus. Okay, so this again this 16C is connected to Vref 16C, and again 8C is also connected to the Vref, and remaining 8C are connected to the ground. Okay, and of course this is grounded. Okay, so now the question is, what is this voltage? Okay, so now this one we can easily find out by using the superposition theorem. Okay, again we can use the superposition theorem here to find out this voltage. Okay, so to do that, what we can do is we can just ground this one. Okay, we'll ground this one. Okay, we'll ground this one, and we just need to find out what is the voltage because of this Vref only. Okay, for that it is again the straightforward. So basically if you see here, these two are coming in parallel. Okay, and this is coming in series. So basically this voltage Vx will be, in this case, imagining all the capacitors are discharged initially, okay, or charge is 0, so it will be 8C, okay, 8C by all this sum up together, which is again 32 C, okay, into Vref. So that means this will becomes 1/4 of Vref. Okay, 1/4 of Vref. Okay, so now because by using a superposition theorem, right, we know that this Vx is already minus V in plus Vref. Okay, or if I just make this also, if I just because now in this case this is also connected to Vref. Okay, then what we need to do is if this is Vref and if this is grounded, we know that previously this is Vref by 2. So now what will happen if I just connect both of them to Vref, so then it will be nothing but the summation of, you know, it will be just summation of these two voltage. Okay, so Vref by 2 and Vref by 4. Okay, so this is basically Vref by 2 and Vref by 4 based on the superposition theorem. So if only this is connected, then this voltage is Vref by 2, whereas only if this is Vref and others are grounded, this is Vref by 4. Okay, so if you see here, we are getting the same kind of comparison, right? Initially we compared with Vref by 2, now we are comparing with Vref by 2 and Vref by 4. Okay, and of course, if again the same thing logic here, if this happens to be 1, that means if V in is greater than Vref by 2 plus Vref by 4, okay, so then this switch will be intact, else we are going to turn back it to the ground. The reason is simple. That's what we had mentioned in the beginning of this charge redistribution based this one. So if it is higher than Vref, okay, that means we are going to the next comparison that we are going to do is Vref by 2 and Vref by 4. Whereas, okay, if it is lower, if the MSB is lower, we are going to do the next comparison only with the Vref by 4. Okay, so that means in this case, if my first B1 is 0, then I am going to come back here. Okay, then I am going to come back here. Okay, and the next kind of comparison that I'll do is only, so this will go off, because as soon as I connect to this to the ground, so this will go off. Okay, this will be grounded. Okay, and this node voltage becomes only Vx becomes Vref by 4, and then we are doing the comparison with Vin with the Vref by 4. Okay, but whereas this is 1, we are going to do the intake. So the same thing is going to, you know, follow. Okay, as we then we are going to check the V3, then V4, then V5. Okay, so this way we are going to, you know, turn on the switches and keep on checking, right, whether it is the output of this comparator is 1 or 0, and if it is 1, we are going to keep this change intact. If it is 0, we are going to go back, something like that. Okay, so if this both of them are 1, we know that this is Vin plus Vref by 2 plus Vref by 4. Okay, yeah. The other thing is, if you see here, we have V1, V2, V3, V4, V5, and we have this S3 or another capacitor. The reason is, I think you must have known now. Okay, we want to keep it symmetric, right? We want the total capacitor to be 32, so that whatever the division that we are trying to do, make here all this one, right, it becomes valid. Otherwise it becomes, right, the total sum becomes 31. So we are not going to get that particular division of, you know, 1 by 2, 1 by 4, 1 by 8, right? Yeah. So this is the overall working of the charge distribution based SAR ADC. So what we'll do is that whatever we have discussed now, we are just going to summarize it as a simple flowchart that we had done previously for the basic SAR ADC. Okay. So this is how it looks like. So we are going to we are going to start. Okay, we are going to sample V in, sample and maybe instead of Vx, yeah, so we are going to make sample and make of course instead of Vx, let me use just V. Okay, V equal to V in. Okay, because Vx is minus V in, right? So just to, you know, differentiate from that, right? I equal to 1. You can use any other variable, fine. So the next thing that we are going to do is we are doing a very basic comparison. Okay, that first we'll say V minus, okay, Vref by 2i whether it is greater than 0 or not, or minus Vx plus Vref by 2I is greater than 0 or not, the same thing. So basically here V equal to minus Vx, okay, and we know that if this is Vr, if this is no, okay, then we know that Vi equal to 0. If it is yes, if it is greater, okay, we know that Vi is equal to 1, okay, and if Bi is equal to 1, then only we are going to update the V to be V minus Vref by 2I, okay, else we are going to update the V, we are going to give the V. So again, next the next thing that we are supposed to do is we'll update the I as I plus 1. The same thing follows like the conventional, SAR ADC. And here we are doing to do a basic comparison again, whether this my I is greater than n or not. If it is no, we are going to continue the loop. If it is yes, we are going to stop the conversion. Okay, so this is the basic flow. Okay, so first we are going to sample and then make V equal to V in. Okay, again I was mentioning that in the other diagram we have used Vx, but this is the same thing. Okay, only thing is that the polarity is different. Okay, so yeah. And then we are going to check V minus Vref by 2I if it is greater than 0 or not. Okay, if it is 1, then we are going to update the V as V minus Vref by 2I. If it is 0, then we are going to keep it the same, V will be the same. Okay, that's it. Okay, so let's take a very simple example again for this case, and we'll end the discussion. Okay. Example. Okay, again let's consider the same example that we had done previously for the conventional SAR logic or SAR ADC. 8 volt and V in to be 5.6 volt. So we are supposed to get the same result. Okay, in the iteration number 1, okay, for I equal to 1, we know that V equal to V in is equal to 5.6 volt. Okay, now V minus Vref by 2I is equal to 5.6 minus 8 by 2 in this case, because I equal to 1. So this happens to be 1.6 volt. So this is greater than 0. So implies my V1 is equal to 1. Okay, and of course therefore my V will be updated to 1.6 because V1 equal to 1. Okay, in the iteration number 2, okay, I is equal to 2. Now V is, we know that it is updated 1.6 volt. Okay, and now therefore V minus Vref by 2 power 2. Okay, so this is 1.6 minus 8 by 4. So this happens to be minus 0.4. This is less than 1. Okay, sorry, less than 0. This is less than 0. Okay, so therefore my B2 will be 0 and V will not be changing, which is it will be remain 1.6 only. Okay, 1.6 only. Okay, so in the iteration number 3, now I is equal to 3, V is the same 1.6 volt. Okay, So therefore V minus Vref by 2 power 3 will be equal to 1.6 minus Vref is 8, and then 2 power 3 is 8, sorry, 8. So this is 0.6, and this is greater than 0. So therefore my V3 is equal to 1, and therefore implies my V should be updated to 0.6 now, okay, because it's 1, okay. So in the iteration number 4, okay, my I equal to 4 and V equal to 0.6, okay. So therefore V minus Vref by 2 power 4, this is equal to 0.6 minus 8 by 16, okay, this is 0.5, so this is equal to 0.1, so this is greater than 0, so therefore B4 is equal to 1, okay. So if you see, I have got the same output, okay. That means my B1, B2, B3, B4 is equal to 1, 0, 1, 1.